Hello and welcome to the Daily Space for today, Friday, January 24th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Today's news starts with a massive explosion. No, I'm not talking about Betelgeuse. It's still hanging out in Orion, refusing to go boom. I'm instead talking about Supernova 2006 GY. Located in the spiral galaxy NGC 1260 at a distance of about 250 million light years. This supernova was one of the brightest ever observed. And for the past 13 years, astronomers have been trying to figure out why. Adding extra intrigue were the 2009 observations from a Japanese team that spotted unidentifiable elements in the spectrum of the supernova remnant. Let me be clear. They didn't see an unknown element. They saw an element they could not completely identify. And like students doing a standard mystery chemical identification lab, astronomers around the world have been trying to find an explanation for this overly bright explosion and those exceptional spectral lines. Recently, a team from the Max Planck Institute for Astrophysics joined forces with the Japanese observers to try and figure out this system. And it looks like they may have succeeded. Let's start with those unknown spectral lines. Spectra consist of three basic components. There's a background continuum emission, a nice rainbow of bright light that is brighter in some colors than others based on the temperature of the system. This is the black body radiation of a star, and in the case of a supernova, is the combined light from any hot remnant and the light from the surrounding nebula. In addition to this rainbow of light are absorption and emission lines that come from atoms and molecules that are getting excited by that continuum emission and other energetic processes. In stars, identifying lines can be a challenge. But you can at least assume all the elements are at basically the same temperature. And guess what kind of atoms and molecules can exist at that temperature? In a supernova remnant, things are a lot more complicated because you have that surrounding nebula with unknown temperatures and composition and energies. In trying to figure out what elements were in Supernova 2006 GY spectrum, they started from the assumption that it was a hot environment where complicated elements are ionized and missing electrons. This simple assumption turned out to be just plain wrong, and, well, it led to 14 years of confusion. It turns out those unknown lines were from neutral iron. According to researcher Andreas Jerkstedt, this low-energy state of iron is typically not seen in supernovae, where the high energies involved tend to strip one or several electrons from the atoms. With those spectral lines identified, the team could calculate that at least 1/3 a solar mass of iron is present in this system. And that kind of iron content only comes from one kind of supernova, a type 1a supernova, where a white dwarf star is overwhelmed by mass from another star falling onto its surface, triggering an explosion. But here's the thing. Type 1a supernova are supposed to be standard candles that are all the exact same mass and exact same brightness. So this raises the question, how is one of the brightest supernovae known also this standard type 1a kind of a supernova? Well, this is where it gets awesome. They think that a white dwarf star was orbiting a normal star that expanded into a giant star, and in the process engulfed the white dwarf. This kind of an expansion is a normal part of stellar evolution, and eventually our own sun will expand and consume Mercury and Venus. Once that white dwarf was engulfed into the giant star, it began a slow spiral into the star's core. While the white dwarf journeyed inward, the star shed its outer atmosphere, puffing off this envelope of material to create a close-in nebula. When the white dwarf reached the star's core, the combined mass exploded, and the shock wave collided with the surrounding envelope, creating, well, the weird lines that were observed. In this case, we have a white dwarf going nova inside another star with the combined mass of the two stellar cores. This kind of a supernova is evidence that pretty much anything that you can imagine probably will happen somewhere in the universe. It's also a reminder that creativity is required to figure out weird systems and to think outside of the box to solve unusual mysteries. This may be the coolest supernova I have ever read about. You can read more about this supernova in an article in the most recent issue of Science. Studying the individual elements present in stars. And here, let me take a moment to show you that supernova. I got so excited by the content, I completely forgot to show you the object itself. Okay, it's not that exciting. All right, going back to the next story. Studying the individual elements present in stars' atmospheres is one of the least glamorous but most data-rich ways we can observe our universe. From figuring out the mysteries of weird events to figuring out the history of star formation, Spectra have a lot of uses, and a team using the Keck telescope in Hawaii recently used its high-resolution spectrograph to find an ancient star whose composition may be enriched by only one or a few prior supernovae. This star, J0815 plus 4729, is mostly hydrogen and helium, and its abundances of most heavier elements like calcium and iron are only about 1/1,000,000th of what we see in the sun. There are 3 notable elemental exceptions, however. Its carbon percentage is 10% of that of the sun, and its nitrogen and oxygen are 8% and 3% of the sun's. This enhancement in carbon, nitrogen, and oxygen tells us these elements were created in greater amounts by the earliest stars. By finding and studying more of these ancient stars, we will be able to build up a picture of how the composition of our universe has changed over time as we see stars of different ages with different compositions. This kind of detailed work is exactly what the team behind this discovery is doing, and we look forward to covering their future results. And before we end today's show, we want to take a look at another paper in the journal Science and remind you before we do that results found in this journal often evolve or go away under further study. But when they're right, these results can change everything. In a material science article, researchers discuss the creation of a new type of metal alloy in which the electrons move between atoms in an organized way rather than acting independently as we're used to. When cooled to close to absolute zero, this mixture of electron-rich elements, including ytterbium, rubidium, and silicon, undergoes an odd transition, and the team observed what appeared to be quantum entanglement among billions of electrons. While this story isn't one of astronomy, it is one that could someday change how we do astronomy. Historically, the world's most powerful computers have often been developed for astronomical research, or at least used for astronomical research. And this thin film of quantum entangled electrons might be the kind of material needed to advance quantum computing. According to researcher Kwomya Si of Rice University, quantum entanglement is the basis for storage and processing of quantum information. This may be the material leap forward needed to advance our computational game beyond Moore's Law. And that rounds out our show for today. Thank you all for listening, for watching. The Daily Space is produced by Susie Murph and is a product of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks to the generous contributions of people like you. Want to become a supporter of the show? Check us out at patreon.com/CosmoQuestX. I will now take your questions and ask that you please at CosmoQuest, or at least put that purple circle in the center in front of your question. Thank you so much for the bits, Chucker Kev. Thank you. Oh, hi. I see you. And thank you, Broken Symmetry. Here you go, Malachi. I'm throwing things to the other dog. Um, okay, let's see. Hanny's Vorverb. It's been a long time. I'm glad you're back. Hanny's Vorverb asks, is that the most quantum entangled particles that have been seen? I think so. Okay, I'm going to work backwards through the chat today. Again, thank you, Broken Symmetry, for the sub. Scrolling. Bad Panda Bear asks, could this type of supernova result in a neutron star or a black hole? I don't know. I need to go look more to read that question. I was just so excited about the fact that you can have such a weird type 1A supernova where basically a star eats a white dwarf and then it explodes. I missed that part of the paper. I'll go back and find out. I'll probably be blogging about this on Medium later today, so I'll try and remember to tag you when I do that. Larry asks, do you think that ingested white dwarf may have had a core of neutronium? If you mean a core of neutrons, no, white dwarfs don't have the required pressure for that to be a thing. Hanny asks, did the nova occur because the white dwarf was cooler than the core? No, it was simply a matter of the masses colliding. The degenerate white dwarf star didn't get heated up enough to puff back out into being regular matter. And when it combined with the mass at the core of the star, that combined mass and the fact that the degenerate material wasn't undergoing nuclear reactions caused the entire thing to go boom. And it was awesome. So something's ringing. What is ringing? That's my boss calling. I need to answer this. I'm so sorry. Abrupt ending.